Hello everyone, my name is Mike Marchese, and this is my final presentation for Principles of Operating Systems. Here's what the memory map looks like in my system. The LCD screen is given the beginning chunk of SD-RAM. Everything after that uses my malloc. On boot, a chunk of memory is given to the file system. Everything after that is allocated as needed. I took a straightforward approach using the block data structure suggested in class and the first fit algorithm for allocation. Blocks that are free or used by the file system are given the process ID of 0. Focusing in on the file system portion of memory, we see that there's an array of file nodes and an array of file blocks. File nodes can have a type of file, directory, device, or pipe. Each node stores some metadata to a file and the index of its first block. Each file has at least one block, and more blocks are chained together as needed as the file grows. If a file is a directory, then its blocks contain an array of directory entries, which each consist of a file name and a node index. Here's an example of what some files would look like on the system. You have a chain of nodes pointing to directories, pointing to nodes, and so forth until they get to the end file. The orange is a regular file, and the yellow is a special file for devices. For device independent I/O, I implemented the 4 standard functions for each type of device, as well as fgets and fputs on top of that. There's also a number of wrappers for convenience for when you know you want to print to a standard stream, or you know you want to print formatted text. The data structure that I used for streams is shown in the lower left. Key components include the device type and the device ID. On the right, you can see all of the device types that are supported, as well as some example IDs for one of them. The modes that are supported are read, write, and append, but so far only the files and pipes are making use of those. For processes, I decided to have an idle process that can't be killed and is only swapped in if there's not another real process that's ready to run. And the startup sequence that I used was to set the current PCB to a fake, already dead process, and then spawn my real processes and kick the system off. And then on the first time the scheduler runs, it just swaps out that fake process and then later on disposes of it. Alright, let's do some demos. I'll start off by simply setting the system clock. Check that. Okay, looks pretty good. Or we could do something simpler. Just leave off most of it and it'll figure it out. There we are, 1980. How about some file commands? Make dir stuff. And then we'll make a file in there. Alright, let's check it out. ls root directory. There's my folder. And then inside it, there's my file. And you could keep drilling in and looking at things one at a time like this, or you could also call the tree command and see the whole file system. So there's all the devices that are set up at boot and a few example files for playing with. I also have a cat command that lets me look at files, so we could do cat animals and we see what's in there, or it can also look at multiple files, so cat animals pom.txt, and then you get the combination of those two files. Alright, now for processes I have a ps command. You can see I've got 0 is the idle process and 1 is the shell. And now if we run a second version I made of multitask, that's non-blocking. So we can do ps and we see it's added a few processes here. I believe if I push this button, that'll kill some of them off. And then we'll just kill the last one manually. There you go. And now I've also got a spawn command that lets me spawn whatever. So that's also non-blocking. Now the LED is flashing. PS. And we've got a new process there, and let's kill that. it stops flashing. For my final project, I did locks, semaphores, pipes, and redirection. I used the special instructions load register exclusive and store register exclusive to implement locks without having to disable interrupts. I made several functions here. There's lock release, which always succeeds, lock try to take, which may fail but returns immediately, and lock take, which tries and yields repeatedly until it succeeds. I then use those locks to protect critical regions inside my semaphores. These operate as you would expect. When a process calls sem down on a semaphore that's at 0, it puts itself in a queue of waiters and blocks. If another process then calls sem up, it wakes the first waiter in FIFO order. Redirection is when you replace one or more standard streams of a process with other targets. You can combine this with pipes to attach the standard out of one process to the standard in of the next. The way I implemented redirection was by adding an optional path argument to spawn for each of the 3 standard streams. For each path, the appropriate version of fopen is called based on the device type, and the resulting stream is added to the new process's control block. So this command is just for demonstration purposes. All it does is take from standard in, capitalize it, and put it back on standard out, and it waits for end of file, which I can do with Control D. Another one that's like that is forward, which just mirrors from standard in to standard out, but with a time delay. So if I type hello, we get 500 millisecond delay between. And it's just doing that with busy waiting, nothing fancy there. Alright, so now we'll get the redirect command in the mix. So here, the first 2 arguments of redirect are what you want to use for standard in and standard out, and then you give it the command after that. So here, I'm just saying use the regular standard in and standard out, which means that this just does what we saw before. No difference. But now let's do something more meaningful. We'll replace standard in with this text file, and then we will make it double spaced. And there you go. And you can also do this with commands that are not paying attention to standard in. It's just kind of pointless. So here, cat doesn't look at standard in, so it's just going to ignore that, do its normal thing, and print the joke. I could also redirect the poem to the LCD screen. Here I'll give it an indent of 15. I implemented pipes as special files, and I gave them the necessary functions to participate in the stream system. They act as queues of characters. Multiple readers and writers are supported per pipe, and blocking is automatic. So a process that tries to take from an empty pipe is blocked, and a process that tries to put into a full pipe is blocked. To use pipes, first you call a function to create the pipe, then you pass the path of the pipe to spawn, and finally you call the pipe manager function. Here's the life cycle of a pipe. In the initial phase, each time a pipe is passed to spawn, fopen pipe gets called, which increments either the readers or writers count on that pipe. Once the pipe manager is started, the status changes to open. At this point, readers and writers cannot be added. As each process connected to the pipe terminates, either naturally or by being killed, fclose pipe is called by the scheduler's cleanup routine. This decrements either the reader or writer count. Eventually, there will be either no readers or no writers and an empty buffer. The manager declares the pipe broken and wakes any blocked readers or writers. From now on, calls to fputc return errors and calls to fgetc return end of file. This allows the remaining processes connected to the pipe to terminate gracefully. Finally, when there are no readers and no writers left on the pipe manager can delete the pipe and return. The redirect command can also understand pipes. Here we're going to read from one file, pass it through a pipeline of commands, and save it to another file. Original, modified. This time I'm going to run redirect via spawn so that it doesn't block and we can look at the processes using PS. I purposely put a slow command at the tail end of the pipeline so that we can notice how the initial processes all finish up, and then all that's left over is the redirect command itself and that slow command at the end. So PS, and there you have it. There's the normal idle and shell processes plus the redirect and the slow command forward. I'll repeat the exercise, but this time I'll put the slow command at the front of the pipeline so we can see how the later processes block. Each line should print out quickly, but there will be a big delay between lines. This is because the indent command is waiting for an entire line to arrive from the slow forward command, and then it processes and passes that data on quickly. Finally, I'll run that same set of commands, but this time I'll make that first process even slower to give myself the chance to kill the indent process before it ever receives a full line. The break in the pipeline will be detected, and each process will be woken up and then terminate gracefully. Indent should be the third new process, so 2, 3, 4, and they're all gone. And that's a wrap. Any questions?